Let's go more in depth on tests and intervals. And one of the most important things when doing a statistical test is going to be interpreting your p-value. Well, p-value is going to once again tell us a conditional probability. It's telling us if the null is true, what is the probability we saw something at our sample result or something more extreme than our sample result. And I always like using examples that we might understand. Like, let's say your friend tells you that they can run a 5-minute mile. Or let's change it today. Let's say they say, my maximum bench is 300 pounds. Okay, so you're telling me, on average, and you say on average, you say, well, I know how to do averages. Let's do it. On average, you could bench your max, a 1-rep bench. Your average 1-rep max bench when you're fresh right here is going to be 300 pounds. Now, in this notation, notice mu naught is equal to 300 because that is the hypothesized value. And with this, we are saying an alternative. We're going to say, I believe the truth is less than this, that your true average 1-pound max bench is less than 300. Notice how the null has the equal sign and everything else remains the same except for the sign, which changes for the alternative that we are looking for evidence of. The first thing is a population parameter, what we're trying to test right there, the true mean 1 max rep bench, and the other side of it is going to be the hypothesized value, which is known as mu naught in this. You simply add a little naught below it relative to the null hypothesis, the hypothesized or value currently believed until evidence otherwise. So what happens here is they sit down, they try to bench. They only bench 295. Well, if we drew this out, we might need to do it a few times to get a mean. So over repeated measures of 5 days, so we do a sample of 5, and there's variation in it. On average, they were hitting 295, let's say. If we drew this out, and this is not the actual drawing, it's just a hypothetical, what we might see, 300 would be at the center of the curve. 295 as a sample mean might be right there. So what is this p-value telling us? It's telling us that if they are a 300-pound bencher, so here's the given the null is true is right here, and our sample result is going to be this line right here, that's the sample results, then the p-value is telling us the probability. So does it look like something like that could occur every so often? You might say, well, they're hitting less. Well, yeah, but it looks like that p-value just visually is by about 30% of the curve. So with a p-value of 30% right here, this person, if they are truly a 300-pound bench presser who can do a 1-rep max of that, then this would occur, a 295 or lower would occur about 30% of the time. I'll tell you there's a 30% chance of snow. You might say, oh, it might snow. Well, it seems very likely, or quite possible, I should say. Not very likely, but quite within the realm of possibility that this person is actually a 300-pound bench presser. Well, what if we took and changed the sign to a does not equals? And so we could do this right here, a sort of unbiased test. It would simply take the p-value and flip it to the other side. Now we're looking at a result just as extreme on the other side, and we simply double it. Now this would have to be based off the researcher's question to start on how we choose the sign of the alternative. The does not equals just simply doubles the smaller of the two p-values. So we could say, well, we definitely do not have evidence to reject the null here, because with a p-value of 0.60, it's very possible that what they're doing is close enough to the truth. The results of 295 seems quite believable given somebody is a 300-pound bench presser. When we have high p-values, we are choosing to not reject the null. We really only have two choices here. We either reject or we do not reject the null. Classical statisticians will say fail to reject. I prefer to say do not reject. Why do I prefer to say do not reject? Well, it's like you go to the mall or you don't go to the mall. Go to the mall or you fail to go to the mall. It's just, people don't talk anymore by saying fail to reject. They say I do not reject the null. And we should change the way we talk stats. Alpha levels and critical values. The critical value is the point at which we reject the null, and it's relative to an alpha level. So when you change your alpha level, you actually change the critical value. So these would be the z's or the t's by which you would reject the null on, let's say, a two-tailed test. These Z's or T's are going to be called the critical value. And when you change alpha, you change how much area is going to be in the tail, either pushing them out for a higher T or Z, which would lead to a smaller alpha level. As in, if we make the alpha level, currently it might be the classic 0.05 alpha. If we were to change it to 0.01, well, then that would increase those critical values up there by putting less area in the tails. And you would see them over here because now there's only 1% area in both tails combined. So this would make it harder to reject the null because our sample result, in this instance, a p hat, because we're using proportions, not means anymore, would have to fall further out, leading to more evidence needed to reject the null. So when we do this right here, we can pick the alpha level. The alpha level is completely decided by the researcher, but very classically, researchers use 0.05. 0.05 is a classic standard for statisticians because it relates to a 95% confidence interval. And the quickest way to test something is to create the 95% confidence interval and see if your hypothesized value, we could call it mu naught, is contained at that interval. And if mu naught is outside of it, you can reject it at the 0.05 alpha level. 95% confidence intervals relate to 0.05 alpha on the does not equals test. Very important right there. So we statisticians love 95% confidence intervals. We also love 0.05 alpha, and they do the same thing mechanically. When you look at how a confidence interval looks, it's 95% inside, and the two-tailed test would be when you draw it and draw 5% in the tail, leaving 5% alpha. Once again, we reject the null hypothesis when the p-value is less than alpha. And I love to say when the p-value is low, reject the null. When the p-value is high, just let it fly. By let it fly, I mean do not reject. So we need to make sure that we know the level of alpha we are doing and also communicate this to the reader. My level of alpha, and pick it. Let them know. Once again, classically, unless stated otherwise, use 0.05. It's the assumed alpha level unless otherwise stated. And then make sure to tell the reader in your explanation, did you reject or not reject the null, fail to reject the null? But what about practical and statistical significance? Well, statistical significance is literally just p-value less than alpha. That's all statistical significance is. Practical significance is the do I care? And this is the tough one because practical is going to vary from person to person to person to person to person. I can't tell you what is practically significant to you. You have to quote the results to the reader. So this is where we get down to the effect size, which is what we estimate. If I told you that attending a job seminar would double your starting salary, well, that's the effect I'm telling you. It's an estimate. I probably don't know that for truth, but I'm estimating or telling you that we would see a doubling of your salary. Well, if this only was with one person, let's go to the small. Even a large effect size might not be statistically significant. Well, Brian, you don't have the data to back that. So if it's not statistically significant, it could just be by random chance that one person who went to the seminar got a doubling of their salary. You might say, it's not enough data for me to believe this. Even though that seems very practically significant, I can't believe this because you don't have enough data to back it. Well, what if I told you this is a 30-minute seminar, and people who go to it see a 2% increase in their salary, and this has been over decades of research. You might say, wait a minute, you have a very large sample, Brian. So now you have a small effect. The effect is like what we're seeing, the data, 2% increase, small effect. But here's the thing. You have a lot of evidence to back this. It's very statistically significant. It's only 30 minutes of my time and my salary's gonna be 2% more. I'm being offered $50,000, they're gonna offer me $51,000. I mean, I know that's not a lot of money, but for 30 minutes of my time, $1,000 each year starting out, I'll take it. I'll go do that 30-minute seminar. You're not saying I will get that. It's just that we've seen this over time and there's reason to believe that this trend might continue. So the effect size is the estimate of the true difference between what we are trying to see right here. We believe that if someone goes to a seminar versus someone who doesn't, there will be a difference of 2%. Made up for this example. But we do make mistakes. It could be wrong. That's always possible with statistics. That's why we don't like words like will, cause, no. Things like that are not what we say in statistics. We have two main types of statistical errors. We have a type 1 and type 2 error. Now, classically, they show this chart in every class. Here it is right here. The type 1 error and the type 2 error. But I have a different way of teaching. Now, watch the numbers, watch the letters. I'll first show you a number, then I will show you a letter. In a type 1 error, the null is this. True. P. And we reject it. Think about an error. If the null is true, you shouldn't reject it. This is where the error occurs. If the null is true, we should not reject it. We should fail to reject it. In a type 1 error, the null is true, we reject it. In a type 2 error, the null is false. That's an F right there. And we fail to reject it. Once again, repeat with me. In a type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject it. Now notice in the type 2, you say an F word twice. In the type 2 error, the null is false and we fail to reject it. Think about that. If the null is false, we should reject it. So the error in the type 2 is failing to reject the false null because we should have rejected the null. It actually works with the classical language, which I'm not a huge fan of, but when you say the type 2 error is when the null is false and we fail to reject it, then you're talking about the type 2 error. If you want, use this chart right here and understand that if you were to reject the null and the null is false, you made the right decision. Or remember that if you retain or fail to reject the null, retain also means fail to reject, and the null is true, well, then you made the right decision. Not the biggest fan of this chart, though. But we have some issues here. The issues we have is when we do our tests, we have what is called type 1 and type 2 error, which we talked about. Well, a type 1 error is super easy to remember because it's your alpha level. So how much type 1 error probability do you have? Well, usually our type 1 error probability is 0.05 because usually alpha is 0.05. But when it comes to type 2 error, that's beta. And I like to remind people 1, 2, A, B. So you've got 1 is alpha, 2 is beta. Beta is simply not 1 minus alpha. This is not the formula for beta. Beta is not 1 minus alpha. There's a lot of calculators online that'll let you find beta. We won't be so concerned with calculating this class. It is very important for a lot of statistical research and the sciences. It's going to lead to a very important topic coming up here in a moment. But once again, if you want to calculate it, use what are called power calculators, which is what we're going to be talking about here next. So what is beta and what impacts it? Well, beta is going to be impacted by 3 things. We have how false is the null, and that is related to effect size. The effect size is going to be the difference between the hypothesized value and the truth. Imagine I were to play basketball against my brother. We're probably about the same skill level. It'd be hard to see who's better because there's a very small effect. But if I were to play basketball against LeBron, there would be, here's me, much, much shorter. There we go. There'd be a bigger effect. It would be easier to reject the null. Remember, beta is the type 2 error. When you fail to reject the false null, you'd probably be more likely to make a type 2 error between Brian and Darren because we're very similar. You'd be like, well, I don't know who's better. And truth is, one of us is better, probably Darren. And with LeBron and me, you could easily reject the false null. So when the effect size is larger, there's a smaller type 2 error. So when the effect size is larger, when there's a bigger difference, it's easier to see and easier to reject the null and not make the mistake where we fail to reject the false null. Well, what about when it comes to the alpha level? Alpha is how much evidence you are looking for. So if you're only looking for a tiny bit of evidence, if you only want the tiniest bit of evidence, which would be actually an alpha level, very high, you make it easier to reject the null. So when alpha is high, it decreases beta. Do remember that beta is not 1 minus alpha, but they are inversely related. So increasing alpha decreases beta. Think about this. If we set alpha to 1, which is ridiculous, we would make it virtually impossible to make a type 2 error. Because a type 2 error is when you fail to reject the false null. Alpha is the percent of time you reject the null. So if you're rejecting the null 100% of the time, basically, then you'll never fail to reject the null. Now, don't do this, because you would make an insane amount of what? Type 1 errors. Type 1 errors when you reject the null and the null is true. Type 1 A type 1 error, the null is true and we reject it. So you would increase your type 1 errors at the cost of less type 2 errors. You don't want to do that. A really great way to handle this is with sample size, though. If you increase your sample size, you decrease your type 2 error. Think about this. The more sample you have, the better you understand your data, the less likely you would be to make errors. This does not impact type 1 error because type 1 error is only alpha. So the type 2 error, when you fail to reject the false null, can be impacted by sample size. Increasing sample size will decrease your type 2 error rate. And do you see a pattern? When there's a larger effect size over here, a larger effect size leads to lower type 2 error. A larger alpha leads to lower type 2 error. This being type 2, and alpha is type 1. And also a larger sample size leads to lower type 2 error, which is measured by beta. All of these, if they're higher, lead to lower type 2 error. And this is super important to us because we do not want a lot of type 2 error because type 2 error is related to the power of the test. Statisticians say power is the ability to correctly reject the false null. I say power is the ability to find results when results exist. Because if the null is false, we should reject it. That means there's something to find. And power is the ability to find those results. So think about this. If you want to find results, you would take a big sample. If you would want to find results, you would make it easier to reject the null. Now be careful, that's sort of cheating. Don't do that. If you want to find results, it's going to be easier when there's a big effect. When you measure two people and they're very different, it's going to be easy to see that difference. Or you could go in and just say, well, if I see the tiniest of difference, I'm going to move my alpha way up that I don't need much evidence. And that's cheating. Don't do that. We don't do that in stats. And then lastly, you could watch them for more time to say, well, maybe I just need to observe this longer to understand the data better, and then be better able to reject the null. So to review, the three things that impact beta are sample size, effect size, alpha, which is type 1 error. If they increase, like someone gets a larger sample, now we don't control effect size because that's just a truth that exists, but if there is a bigger effect, then that's also going to be something that's going to decrease beta. And also alpha we do control, but we prefer to always keep that at 0.05 to be doing good stats. That is going to decrease beta, and then that is going to increase power, which is measured by 1 minus beta. The power is simply not making a type 2 error. Think about this. If you don't make a type 2 error, then you reject the null when you should, because a type 2 error is failing to reject the false null. So the important thing to know is that every one of these is positively correlated with power and inversely correlated with beta. Larger sample, lower beta. Larger effect, lower beta. Larger alpha, lower beta. Larger sample, more power. Larger effect, which we do not control because we can't control the truth. Larger effect in what exists in the data, higher power. Larger alpha, higher power, but messing with that might not be fair to how we do good statistics. If you want to go more in depth on this, there are power calculators online to figure out the exact power for tests, and many different classes will teach you about that and have you figure out the power. You might say, why would I want to figure this out? Well, when you think about what power means, if we calculate power and we get a power of only 0.00001, this would be 10, 100, 1,000, 10,000, 100,000. This means if results exist, taking our sample would only allow us to find results 1 in 100,000 times. The ability to find results here is not there. If results exist, we would only find them 1 in 100,000 times. So if we're doing this power calculation before collecting data, which a lot of times people do, it's probably pointless to collect data, because even if results exist, we probably wouldn't see them. We'd probably get a type 2 error. If we run a power collection or power test before collecting data, and we got the power equal to this, this means if results exist, we would find them 80% of the time. It means we would make a type 2 error, fail to find the results that exist, fail to reject the false null 20% of the time. So would it be worth our time? Probably, because if results exist, now we haven't even collected data. We don't have any data. We said, well, what if we have a sample size of this and we estimate the effect to be this and we use the alpha of 0.05? Well, if results exist, we would find them 80% of the time. So I think we could probably find results. I mean, we're not promised to find them if there are results, like the ability to reject the null. We're looking for some evidence of something. If there is truly that result, we would see it 80% of the time. Power tests are done to see if you should collect data before actually collecting data. They save time and money and are super valuable to a lot of disciplines.